Hello everyone and welcome back to our reading. Today we're having a small interlude from where we were last time. We were talking about conic extensions, and I had this idea where I would talk about something from topology, uh, in particular talk about simplicial sets. And this is a notion that I want to have in our toolbox so that we can come back to it over and over and over again. I'm not going to talk too much about actual conic extensions in this video, although I'll say a little bit at the very end about sort of how you can generalize simplicial sets and how conic extensions arise in that setting. But mostly what I want to have is an opportunity to fit together a whole bunch of details that we've kind of thrown around from the last couple sections and make an example that's a little bit less toyish. Like in practice, one thing that happens a lot when dealing with conic extensions that I've noticed as I've been reading is that lots of conic extensions are extensions by the Oneida embedding, or extensions of the Oneida embedding. I'm not really sure what the correct terminology is, but none of our examples from the previous videos did this, and that's because the Oneida embedding is a little bit difficult to understand, and so it's sort of not without good reason. But because topology is such a rich source of examples for phenomena that we're going to be learning about, it seems like this is a good time to take some stock and actually learn about the building blocks for topology as viewed from a category theoretical perspective. I guess in other words, I'm saying we'll be slowly introducing ourselves to some of the notions of homotopy theory, although I myself do not know very much at all about homotopy theory. So this will be a learning experience for everybody. Sorry, that was my charger coming unplugged. Okay, so to say what a simplicial set is, it seems that everybody starts by first talking about semi-simplicial sets. So I'm going to follow suit, and I'm going to introduce a category, which is usually denoted by delta ing, in short for injection, as we're about to see. This is the category where the objects these are finite sets that are totally ordered. And the morphisms in this category, these are the order-preserving injections. And in case you forgot, one place that I got stuck while thinking about this is totally ordered doesn't mean that for every pair of elements, this. It means this. Well, I guess I should say, or the other way around. But the point is that equality is possible. So you might ask, when you saw that, you might have said to yourself, wait a second, what's an order-preserving injection? Isn't that automatic? The answer is no, because you can have functions that send pairs of elements where you used to have this, and in fact you had strict inequality. They can be sent to things that have the same value. That's fine, because that still preserves the order. Okay, so this kind of thing can happen, and these are things that we're going to see, or in a moment we're going to eventually drop that, and then life will be a little bit more familiar. Okay, so off the bat, a remark is every totally ordered finite set has a smallest element using the just look at it theorem. You just search for the minimum by comparing things one by one. And so every object is isomorphic to the object n, where this is just the totally ordered set on n elements where you have 0 and then, or this is n plus 1 elements, where you have 0 and then 1 and then 2 and then 3 and then so on. Now, something else that we have in this category, a feature, is that every morphism factors through what we'll call face maps. These are usually denoted by delta I. And what the delta I do is delta I of j is defined piecewise. It's just j if j is less than I, and it's j plus 1 if j is bigger than I. Oh, I'm missing an equality sign, or an equal sign as a possible case somewhere. Where does this go? I'm pretty sure it goes here. I might go back and have to switch that around. It's opposite another set of maps, which are called degeneracy maps. and we're going to see those in a moment, but I'm getting ahead of myself. Okay, the important thing is that every map, once I've used the isomorphism to regard my objects as these canonical totally ordered sets, then every map is a sequence of compositions of these guys. In other words, all that matters is where the gaps are. So like if I have like 3 points and 4 points, the only maps between these, the only question is which one am I skipping for 3 and 4 points? And if it was bigger, if I had like 3 points and 5 points, and it's which 2 am I skipping, and so on. So in other words, it's the inclusion, in this case, this map is the inclusion of 3 into 4, or sorry, 2 into 3, because 0, followed by delta 1, which is a self, we're applying this as a sort of self map here. No, that doesn't make sense. I can't apply that as a self map. What I have to do is first, in fact, this just is the map delta. Okay, I see. This is just the map delta 1 because it skips over. We send 0 to 0, and then 1 goes to 2. So this is delta 0. I'm doing a great job today, guys. 0 goes to 0, and then 1 is bigger than 0, and 1 gets bumped up. So that's what this map is. And if I had more points, then I could make more complicated things. But I think you guys get the gist, that every time, if I wanted to map into some bigger set with more gaps in it, then I could just first apply this guy at the first gap, and then I could continuously include / take deltas maps in order to make whatever the correct configuration is. Okay, now the way that you want to think about these things is these objects are sort of like combinatorial versions of topological features. And we've sort of seen that before if you have some experience with simplices, like classical simplices, like simplicial homology or so. That's going to be the sort of inspiration for all of this stuff. What we have to struggle with is that simplices sort of suck because they're sort of combinatorially bulky. The problem is that, like, to make a sphere, for example, the simplest structure I know on a sphere, probably the simplest one, period, looks like this. It's a tetrahedron. And this involves 4 faces. And I don't know how many edges. Looks like 6 edges. But yeah, the Euler characteristic is a thing. 4 vertices. And on a torus, I'm not even going to bother to write it down because it's a lot. It's a theorem that you need 7 faces. And this has to do with the embedding of the complete graph. The complete bipartite graph, K33. And you can show that you can make a simplicial structure on a torus, but in general, simplices are bulky, sort of contain too much data. I'm really far ahead of myself. I didn't make a definition. I didn't make the actual definition of what a simplicial set is. So a semi-simplicial set, right? So what I said when I defined this category, but I didn't define what a semi-simplicial set is. So a semi-simplicial set is a functor delta op to set. And so this is sort of how you regard this as a simplex. You sort of map these guys into actual sets, and then you think of them, the combinatorics of the abstract category in some specific set, as sort of carrying the actual data. And if you're not familiar with simplices in the usual way, basically what I want you to have in mind is just the following 2 rules. A simplicial complex, the kind of thing that we're generalizing here, these are objects that are built out of vertices, edges, faces, all made of triangles, and they're higher dimensional analogs, subject to the properties that if 2 faces meet, they coincide. In other words, you can't have like a triangle and then like another partial triangle overlapping it. Like things have to meet face to face and edge to edge and so on. And also, every face of a face is a face. Which is a complicated and funny sounding way of saying these things are closed in a descending order. So if my triangle looks like this, right? I can't just have this triangle. I have to have its boundary. The faces of the triangle, the edges and the vertices, also have to be faces of my simplicial complex. So I need those two. And these closure properties are basically the key in general. And then the other stuff like the total order, these exist to make certain homological algebra computations make sense. And we're going to talk all about all that later in this video and in future videos. So don't stress about it. Okay, so the problem then, right? We've said that semi-simplicial sets are sort of like analogs of classical simplices. Those are really bulky, sort of hard to work with. And the reason is basically boils down to this necessity that these things be injective, sort of captures the idea that I can't have any like ridiculous faces. Like I can't have an edge, a face consisting of just an edge and such. But that is a thing that we do quite a bit in algebraic topology. Like when you learn about, instead of simplicial homology, you learn about singular homology. Then you allow wiggly boys as your simplices. That might look like this. This might be a face of something. But I also can allow this as a face where I collapse this thing down to here and I just think of the whole thing, this whole edge or this path, as being a face where I have some parametrization of this thing that looks like this, and I'm just constant along these vertical fibers. And so, just like in algebraic topology, where singular homology ends up being the one that's sort of the most useful, and all the other homologies sort of are instantiations of singular homology in different settings, simplicial sets, what you get when you toss out the injectivity requirement, are the things that are sort of the cornerstone of this homotopical notion. So I'll make that definition. It's very much the same as what we just saw before. Now we just call this category delta, and this will be all finite. I don't know. Did I require non-empty above? I don't remember. Let's see. Total order finite sets. I don't think I did. I'm actually not sure now if in the world of semi-simplicial sets that we allow the empty set, but we're definitely going to bar it here. So I'm going to explicitly exclude it here. I'm not sure that it matters. The important thing is the objects are the same, but the morphisms are now allowed to be anything order preserving at all, including the non-injections. And the important thing about this is that in the first situation, all the maps had to go from smaller simplices to higher simplices. Like basically all we could do is make inclusions. But now we can make maps that go in the reverse direction. So these are called degeneracies. We already talked about the delta I, but now we have maps sigma I, which after using some isomorphism go from n+1 to n. And these are defined by sigma I of j is, again, piecewise defined. It's just j for j less than or equal to I, and it's j minus 1 for j greater than I. Okay, that means I was wrong when I defined the deltas above, because I put the delta, it's the opposite case. So I apologize for that. This is new. Like I said, this stuff is new to me. I'm also learning. So yeah, they should be opposite each other. And this means that we have quite a handful of maps that are possible now. Like, for example, I can send 3 to 1, and remember this has 4 points, 2 points. I can send this guy here, and then this guy can go here, and then the last ones can all go to the same place, and that's order preserving. I also have a constant map sending everything to just the first point or everything to just the second point. Or I can make any combination of things where I send a couple things to the first point and then a couple more to the second point. It's also fine. All of these are fine. So there's quite a bit more maps now. And of course, continuing the trend, a simplicial set is a functor. delta op to set. So, you know, these are just our sheaves basically. These are our pre-sheaves of on the category delta. And I think actually Kashiwara and Shapira mentioned them in the chapter 1 exercises. They may not call them that, but they definitely introduced this category. Okay, so now let's make some examples. I'm going to show you 2 examples. Example 1 is the easiest easiest simplicial and semi-simplicial sets. So for the easiest semi-simplicial set, it's actually a really simple thing to describe. We just take the functor, which on delta 0, in other words, on the associated to the objects that have only one point, then we have f from delta 0 to set, which consists of just a singleton, like so. And then for all the higher guys, we just make this go empty. Excuse me. This is often denoted with like an x0 instead of f. So then I would just write, or maybe what I should say is x0 is this guy. And then all the higher xi's, these are empty sets. I see. So then actually we allow empty sets then, or at least we allow mapping to the empty set. Okay. Anyway, this is a semi-simplicial set, and we can make sense of this because the delta j, these go xn to xn minus 1, and we're fine here because we always have the empty map. So it's possible to make this functor make sense. But we can't make it make sense simplically because the sigma j's go the reverse direction, and then you're trying to map into the empty set. So now we're out of luck. So instead, the simplest simplicial set has to be non-empty in every what you might call degree. That's what I'm going to call it. I don't know if this is normal algebraic topology language, but it sort of captures the idea from simplicial complexes where you would talk about like skeleta of a complex. So I'm going to call them degrees. The simplest simplicial set then has to be non-empty in every degree, and so we'll take the singleton in every degree. So we'll declare xi to be a single point in each degree. And now we have to say what the deltas and the sigmas do, but there's nothing for them to do except be the constant map. So all the delta I, sigma I are the respective functions. And that's the only thing they can be. And if it's not clear yet what sort of space this thing represents, like if your idea is you're still thinking about semi-simplicial sets, so you're thinking about these like simplicial complexes, you might think that this object has like a simplex in every dimension, a single simplex in every dimension, but that they're somehow degenerate because, like, you know, if I had a legitimate edge, I would have 2 vertices and such. So maybe you think like, okay, that edge is attached to itself in a loop. And then you have more trouble. Like, how do I make sense of the face? Like, what's going on with the face? Don't worry. In just a moment, I'm going to talk about this notion of what they call geometric realization. And then with geometric realization, we'll be able to make a recipe for how to understand these things in the case that you can't visualize them. And that will give some insight. Okay, so let's do example 2. This is another example that's sort of a little bit more theoretical, but also very important. What I do is I think about the Unita embedding. I look at my embedding from delta into delta op to set. This is our Unita embedding. And so this tells us how to regard each n in this category is itself a simplicial set. And what's going on, right? If I look at xm for some m, then this is by definition hom in the delta category from M to N. And I want to understand what this is. So first, a name. We call this the standard simplex. So the Unida embedding gives us a way of capturing what we'll think of as the standard simplex. And let's figure out what this is. So what's x0? Well, x0 is hom in delta 0, n. And so this consists of n plus 1 points, n plus 1 maps from 0 into n, just given by a choice of where I put these guys. So we would draw that, a bunch of points, n plus 1 points. x1 is then hom, again in delta, from 1 to n. So then this is slightly harder to choose how many points there are, but if you know a little combinatorics, it's just n plus 1, choose 2 maps. Oh, actually that's not quite right, because it depends on where I choose the first one. So at first I choose the first one. Yeah, it's not symmetric. I choose the first one, and then whatever that choice is, I can only pick from the ones that are smaller than that. Or, sorry, bigger than that. So I have n plus 1 choices for the first guy, and then however many I pick, whatever I pick, it's only the things that are above that. Is there an easy formula for that? Am I just dumb? Yeah, it's the upper triangle. So it's n times n minus 1 over 2 choices. Well, maybe this is the combinations formula still. Anyway, I don't want to think about combinatorics. It's very late at night where I'm recording, and I'm tired, so I don't want to think about this. The important thing is that these now, we think of these as like edges, where they're connecting from lower to higher vertices. And this pattern continues all the way until you get to xn, which, oh, I see. It's because there's degeneracy, so it's not n times n minus 1 over 2, because that's still wrong, because I can pick the same guy twice and I can have a degenerate. So I'm not going to try to count this. I'm just going to write maps 1 to n. This is hom nn. And this, we think of these things as recording in each step. These are things like vertices, edges, and then these are the top dimensional cells. But then what? Well, the pattern continues, right, in the sense that we're still looking at maps. But the question is then, how do I think about these? How do I think of these geometrically? And that's the question that I'm now about to answer. So we're going to talk about geometric realization. So recall, for those of you who have not seen this ever or not seen this recently, that the standard geometric simplex, also, just like while I'm writing this, I'm going to go on a rant. I disagree that this is a geometric notion. I am a differential geometer at heart, and for me, this is not geometric. It's more like embedding a simplicial complex in space. So, but you're not using anything geometric about it, right? You can sort of still do topology on these things. This is the set of numbers xi, all in 0, 1, such that the sum of the xi is 1. So what's that look like? Well, in dimension 2, for example, I have this point 1, 0, this point 0, 1, and everything on the line is an example. So this is a 1 simplex. And then if I go up a dimension, then we get 3 points here like so, and their connection is that little triangular piece of a plane. That's a 2 simplex, and so on. Okay, now the geometric realization. What we do is we define, it's usually denoted by x lower dot. I take a disjoint union over all of the xn's, which are sets, times delta n. These are the standard simplices. So in other words, for every element of xn, I should call this delta n, upper n, just notation, but should be consistent. For every n and every point in this guy, I take a simplex. So now I have this collection of simplices in each dimension. Now I have to put them together. I glue them together using the combinatorics of the simplicial set. So I take these, I have these guys partial I, x. These are the image of the di's in the category of sets of the delta i's in the delta category. And whenever I have, and I glue this way. So for every delta I on the categorical side and the delta side, I glue this to the image thing, the di's, the partial i's, on the geometric side, so to speak, on the space side. And similarly, I make the exact same convention for the degeneracy maps, where for every SI, the image of a sigma on the set side, I glue this to the corresponding combinatorial degeneracy map. So in other words, this is the usual procedure for sort of stitching together a simplicial complex. I have a bunch of abstract simplices, and then I specify what edges and faces are glued together. Well, I guess an abstract simplicial complex would be like an abstract simplicial set. It's just some totally ordered set with some subsets satisfying those closure conditions. But this thing is the analog of the geometric realization of a simplicial complex in that setting, where now I'm using the combinatorics of the simplicial set in order to cook up this topological object. An important thing about this, for topological reasons, we're not going to need these facts, or this fact I should say, is that you have to be a little bit careful about the topology. Because on one hand, on any given simplex, you have this subspace topology, but this thing has the quotient topology. Which can sometimes be a little bit different than you expect. Like, there are all sorts of hiccups in homotopy theory where people are like, no, this category is no good, so we work with this other category where the spaces are a little bit nicer because the quotient topology there coincides with some other nice topology. Like, there are messed up examples like infinite wedges and things like that that can make arguments go wrong. I'm not an expert on this stuff. I remember I sat in a class on this topic early on in my grad school career before I knew that I didn't know any topology. Of course, I know some topology now, but at the time I didn't. And there was a student in the class who got into not an argument, but like a discussion with the professor about some counterexample along those lines with some non-compactly generated space. And if you're a topologist, you know what I'm talking about. But if you're not, then you don't. So I'm not going to dwell on this. Let's do something useful and take our examples and figure out what the geometric realization is saying. So in the first example, I have a simplex in every dimension. So I have a point and an edge and a face and so on. And then how do I glue these together? Well, I start with the point. Of course, there's nothing to say about the point because there's no meaningful maps that I can use there. But I can use at the edge level, I can sort of see what's going on. Because in degree 1, I know that I have a single element, which is just that, I'll call it the asterisk, maybe like this star guy, in degree 1. And so I take this edge, but I know that SI of my asterisk for any U in the simplex, so for any point in my edge, is glued to the asterisk. This is now in a different dimension because the sigmas go down. So this will be now sigma I U. And so the point here is that everything in my edge is glued to a point. So the whole edge is collapsed. So actually that degree 1 thing provides nothing new. And similarly, for all the other guys, you can now argue by induction if you like. And so what this means then is that everything in sight is being collapsed, and you have just a point. And now that I've said this, it's actually clear that this thing where I have star in every dimension, that's actually just the standard simplex 0, right? After doing the UNITA embedding, because hom delta I 0 is just a single map for every dimension, because there's only one thing to send it to. It's a single point. So even without the order stuff, right, there's just only one thing to possibly send it to. Okay, so this is telling us then that this is the standard 0 simplex, just a point. Now let's go back to the other example where we started drawing the standard simplex and figure out what's going on here. We said what was going on. We sort of understood the vertices and the edges. They had some degenerate edges. We had some non-degenerate edges connecting things from low to high. But now the main question is, what's going on in the higher degree stuff? Well, if I look at xm, hom delta from m to n, this also has to be degenerate. So all the maps are now degenerate. And so very similarly, the argument we just saw with the degenerate maps tells us that if I have a point in some alleged higher simplex, it must be glued to something else, because that map being a degeneracy is sigma of something. So in other words, any such map, maybe I'll call it phi, is sigma I of some psi. And that in turn means that the degeneracy relation lets me glue that down to something lower. So nothing new is added in these higher degrees. And so we knew how to visualize the non-degenerate simplices. In the lower dimensions, a degeneracy doesn't matter. Like a degenerate, say, face on a 4 simplex doesn't do us any harm. It's just we already had it accounted for. But the higher guys, those being degenerate, means that they're gone and they don't add anything. So this tells us that this really does capture our idea of the combinatorial nature of a standard simplex, because we sort of eliminated everything from the high degrees that was otherwise mysterious. Okay, now here's an important proposition. This video is already 30 minutes long, so I don't know if I'm going to prove this or not. Maybe I'll try to sketch the proof. I can't tell you the proposition until I tell you the other definition. So we have another functor. We have a functor which, geometric realization, which eats a simplicial set, gives us a space. However, we can also go the other way around. We can start with a space and we can get a simplicial set. And this is what you do in algebraic topology when I already have a space and then I start looking at, I want to construct a singular chain complex, for example. I take all of my maps from simplices into my space, which includes the degenerate ones. And that gives me, well, a chain complex, but in particular, a simplicial set. So we define the functor, well, the functor is called sing, but sing x in particular, is the simplicial set, which is defined in every degree by sing x in degree n to be the continuous maps from delta n to x. In other words, this is just functions from delta n into x. This is, if you remember, this is how you set up the singular chain complex, because then we can use those boundary maps to actually construct a differential. That's going to be useful in a moment, so keep that in mind. Now the proposition is that geometric realization and singularization are an adjoint pair. Get denoted like this? I think so. And I think geometric realization is often just denoted by absolute value bars. Singularization, I forget. I want to say that singularization is related to taking the nerve and that was often just called n, but I'm not willing to gamble on that, so I'm not going to write that down. Of course, what I mean here is that these are an adjoint pair. Okay, so the way that you prove this is it's kind of a computation. What we do is we basically just calculate what happens to all of the various morphisms, and we're just basically checking that the isomorphisms we want are actually there. So maybe I'll get started and see how far I can go. I feel like every good talk needs a proof. So let's say that we have phi from x to sing y for some x and y. What does that mean? Well, phi is a collection of morphisms phi n, xn to hom delta n y. And that in particular, these things have to satisfy, and I'll elaborate on what this means in a second, phi n of s set x f xn. The parens here are annoying, so I'll explain this formula in a second. F phi n of xn. I hope I got all my parens right. So what does this mean? So first, S set, simplicial set, is, in particular S set x, is the functor which just regards x as a simplicial set. So nothing really special going on here. F, in our category, we had this remark in the beginning that every morphism can be regarded as a sequence of inclusions and some deltas. Well, in the simplicial world, you can say something similar, except you also have degeneracies. So F is a composition of boundaries and degeneracies. And every map can be written in this way. Then, by definition of our singular chain complex, then, what we know is that S set sing y of f applied to some pi. This is just, oh, there's a typo in my notes. That's unfortunate. Give me a second. I'm going to have a think about this. Make sure I get this right. What's going on here? I think I'm just missing a pi. Okay, so this should be pi composed with the functor space, and of course this is the functor which just sends an n simplex. Well, maybe what I should do is I should be clear, because otherwise that formula is going to look weird. This is the functor that sends n in the delta category that actually realizes this as the standard simplex. And now pi, this guy is our map, delta n to y, some element of this sing yn. Okay, so in order to make this argument work, we define a capital phi, and we notate it as phi xy for the sake of clarity. And I define phi xy applied to little phi to be the homeomorphisms which take xnu to phi of xn applied to u. And the very first thing you have to do is actually check that this makes sense. The problem is, of course, the identifications, like the various gluing relations. Now, it's not that bad, though, because 2 points can be glued together only when there's some sequence of degeneracies and boundaries, which we're calling f, so that S set x of f applied to xn is actually xm. And similarly, for the u's, we would need space delta f um to be un. So all we have to do is actually check that this thing works out, and then I get the same thing. So let's check what happens with phi of xm applied to um. Phi xm um, this is our definition, is that this is S set x of f xn applied to un, and this is the same as S set sing y phi xn of so we managed to switch the first guy over. This in turn is phi xn of space delta f and this in turn is phi xn un. So we're good. And now we need to check the naturality. I'm just going to do this once. I'll do the argument on y, and the argument on x will be sort of similar but different. And then I think that will finish us off. So for naturality, suppose we have a g y to some y prime, a morphism of spaces. So this is on the topology side. And now we have x to sing y. So then sing g applied to phi, this is the morphism x to sing y, which is defined by the following formula. We have sing g composed with phi. This eats two arguments, which is a little bit annoying, but hopefully it's clear. Like so. I feel, parens are a little bit mismatched. Phi x. I think it should be like this. Parens are confusing. And so now, what is our capital phi of xy prime? Well, this thing is just the map, which takes xn un and sends it to g of phi n xn un. But this is, of course, equal to g composed phi xy applied to phi. Okay. The argument in the other direction is very much the same. So I'll skip it because we're already 45 minutes in. I'll just write the other features of naturality are similar. Okay, so what's the first takeaway of all this? This is a very interesting example of an adjunction that's not, like the forgetful free. So it's a new example of an adjunction. I mean, the only examples that I've really hammered so far in our talks have been forgetful free and tensor hom. So this is something completely new. But the second thing is that there's actually not much really special about the category of sets in what we've been doing here. I can replace set by any other category I want. That category should be co-complete so that we can make sense of everything that we need to, but otherwise it doesn't really matter. And lots of categories are co-complete. Like, for example, groups, well, abelian groups at least. I'm not sure about all groups. Maybe there's like nasty problems with monsterly generated groups otherwise, but certainly abelian groups and other algebraic widgets. But also there are categories like manifolds and Lie groups, for example, are all co-complete categories. So you can speak of simplicial objects in any such category. And this gives you interesting questions then. Like, first, what are these simplicial objects? Like, what do they look like? How do they behave? But also, how do things like geometric realization or singularization work in these categories? Well, there's a sense in which singularization is easy because the definition we made is just a certain hom, right? You have to change the category you want, but the right adjoint of the generalized adjoint pair will run e to the simplicial sets, which just takes whatever my object is, and I send it to hom in E. Like so. And so this is not going to at all be a difficult thing to construct. But geometric realization is sort of interesting, right? So like, what is the correct replacement for geometric realization? And here we can say something about conic extensions. So the idea is we have this Unita embedding that takes our category delta into its functor category, like so. And I'm going to denote that by gamma. And then let's say we wanted to deal with simplicial groups, or simplicial abelian groups. Then I could map that into abelian groups this way. And then the thing that should play the role of geometric realization will be the left adjoint, or sorry, the left conic extension. Along the Unita embedding. And this is sort of not so easy at first glance to get your hands on. In fact, I don't know a general procedure for understanding what the analog of realization looks like. I know there are some higher categorical descriptions, like maybe later on, if we talk about two categories ever, we could talk about coends, which is a concept that we've sort of encountered already because we've talked about the universal way to view limits and colimits. So we have the machine to talk about that. I'm not sure if we will, but that's one way. But in practice, I don't really know any immediately straightforward way to figure out what this thing looks like. However, for abelian groups, I can sort of tell you what it is because we can sort of inspect and see what's happening here. And I think this might also work for, sorry about that, that's my laptop wanting to update. So for groups and maybe for rings, we can figure out sort of what this is. I'll just do groups because it's the one I know I can do. I just think I can do rings, commutative rings, that is. What's going on here is our functor, which I'll call G, has to take all of the objects from delta into ab, and we said all those objects are isomorphic to something in the standard simplex. So that means we get a family of groups. So G's image is a countable collection of groups, which we could call GI. And we know that the functoriality, we have these morphisms DI, which run, or maybe I should call them DN, GN to GN minus 1. And we also have some S maps, which go in the reverse direction. But the important thing is these guys, because the usual proof that d squared equals 0 still works on a simplicial set, right? If I define, I didn't tell you what d is. If I define d to be our usual alternating sum of the di's that you could get by omitting the various faces. This actually notation is confusing. This dn here that I wrote here is not quite right because for every n, like in any given degree, the face maps, there are a bunch of different possible face maps. So I should maybe write, well, I'm not going to try to get the notation completely right, but the idea is that for a given fixed n, there are a bunch of di. So maybe I have something like this, gn to gn minus 1, like a whole bunch of them, and then I sum over them. Then the usual proof that d squared equals 0 works, because the different faces, each of them miss one, and so everything happens to get missed in such a way that you get opposite signs and things cancel. And so the structure of the di's gives rise to these delta, in fact, maybe I'll call them delta n's to be clear, so that we acquire a differential, and that the image of G is actually a chain complex. So in other words, what we figured out here is that chain complexes, well, at least that every simplicial abelian group is a chain complex. But actually, the reverse is also true in a suitable sense. You have to work a little bit to make sense of this, but there's this idea called the Dold-Kahn correspondence. Which basically says a stronger version of this. It says that as categories, simplicial abelian groups is equivalent to chain complexes. Of course, these are over Z modules. Okay, so this sort of thing can be interesting. There's quite a bit more that one can say about these notions, and so I make no claims of saying everything that one can say or being comprehensive in any sense about conic extensions and these notions. What I will say is that I want this to be a sort of starting point for us, because a rich source of examples in category theory come from building on these ideas. Of course, you can move in the direction of infinity categories, which we might have to say some things about here and there to get sort of deep into this stuff. But we want to have tools to talk about things like principal bundles, for example, are a direction that we can move along these lines, and classifying spaces for, of course, for groups, but also for categories. And so I sort of wanted this to be a introduction to these ideas so that we'll all sort of be familiar with them. So when we want to have more distraction videos coming from topology, then we're well equipped to talk about all the different categorical and topological ideas that we'll need for those various settings. Okay, I think this is a good place to call it. So in that case, then I'll be picking up next time where we left off and actually continuing to work through Kashiwara and Shapira. And I'm looking forward to plowing full speed ahead through the rest of Chapter 2. All right, take care, everyone, and I'll see you all in the next video.